In this lesson, we're going to be talking about how to find absolute extrema on a closed interval. So we've learned previously that relative or local extrema occur at critical values, and that absolute or global extrema can occur at critical values or at endpoints of an interval. Just a side note there at the little asterisk that some textbooks and curriculums might define these a little bit differently. If you're following along with these notes and these videos, we're going to be using this definition. So therefore, when we're determining absolute extrema, we have to always consider that they might occur at the endpoint. If you take AP Calculus and you're taking the exam and there's a question like this, they generally have on the rubric that worth a point is noting that you addressed the endpoints of the interval, not just the critical values. Let's take a look at a sample question. Number 1. We're going to find the absolute max and min of f of x equals x squared plus 2x on the interval negative 2 to 2. We're going to start out by finding our critical numbers, and we do that by taking the derivative, setting it equal to 0, and solving. So when I do that, I got negative 1 for my value of the critical number. Now what we're going to do is we're going to make a little table of values, basically comparing the y-coordinates, or f of x, for both the endpoints and the critical value. So that means I'm going to look at negative 2, negative 1, and positive 2. So these are our endpoints, and then the negative 1 is our critical number. So what we're going to do is we're going to find the y values, and we're plugging them into the original function. We're talking about the absolute min and max of f of x. So if I plug negative 2 into the original function, x squared plus 2x, I'm going to get 0 as my output. If I plug in negative 1, I'm going to get negative 1 back. And if I plug in 2, I get 8. So this basically tells me that f of x has an absolute max of 8 that occurs at x equals 2. And it has an absolute minimum of negative 1 that occurs at x equals negative 1. All right, let's take a look at number 2. F of x equals x cubed minus 3x on the interval 0 to 3. Let's start by taking our derivative to find our critical numbers, setting it equal to 0. And when we do this, I'm going to get x equals 1 and x equals negative 1 as my critical numbers. Well, negative 1 is not in the interval that was given to us, so I'm not going to consider that as an option here. So when I make my table of values, I'm only going to look at x and f of x for 0, 3, and then our new value of 1. So what we're going to do is we're going to take each of those values and we're going to plug them into f of x. Remember, we're always plugging into the original function here. When I plug 0 into the original function, I'm going to get back 0. When I plug in 1, I get negative 2. And when I plug in 3, I get 18. So I know that this graph has an absolute max of 18 at x equals 3. And an absolute min of negative 2 at x equals 1. Okay, for number 3, we have a trig question. So f of x is sine 2x, and we're looking at the interval 0 to pi. So let's start by taking our derivative. We're going to get cosine of 2x times 2, and we're going to set that equal to 0. I'm just going to move that 2 to the front. And we're going to solve for all values of x that this would be true for. So I could divide out the 2 on both sides. And then to help me with the rest, I like to refer to my unit circle. So when we have cosine on the unit circle, that is referring to the x value. So we're looking for the x value to be 0. And that happens here and here. So x equals, or cosine equals 0 at pi over 2 and 3 pi over 2. However, we're looking at cosine of 2x, so we have to take that into account. So we're looking for where does 2x equal pi over 2, and where does 2x equal 3 pi over 2. This is going to give me pi over 4 when I solve for x. This is going to give me 3 pi over 4, and those are our two critical numbers. Okay, so again, because of the fact that this is cosine of 2x in here, we have to take that into account. All right, so now that we have that, we're going to make our table of values, and we're going to use our endpoints, 0 and pi, and then our two critical values, pi over 4, 3 pi over 4. And if you ever need more time in the video to fill in the y column or do anything else, copy something down, remember you always have the option to pause the video and then resume when ready. So I'm going to plug 0 into the original function. That gives me 0. When I plug in pi over 4, I'm going to get 1. When I plug in 3 pi over 4, I'm getting -1. And when I plug in pi, I get 0. So this tells me that there is an absolute max of 1 at x equals pi over 4. And there's an absolute minimum of -1 at x equals 3 pi over 4. Okay, number 4, we're looking at f of x equals 1 over x plus 2 on the interval -3 to 0. So we're going to take our derivative here. You have a couple of options on how to do that. You can utilize quotient rule if you want, or you could rewrite this as x plus 2 to the -1 power. When you take the derivative of that, you would be bringing the -1 down in front, subtracting 1 from the exponent, and I'd multiply by the derivative of the inside, which is 1. When I rewrite this and I set it equal to 0, this gives me -1 over x plus 2 squared. All right, so if we take a look at that, and again, if you had done quotient rule, you would get the same answer. I'm going to find where the derivative is equal to 0 or where it doesn't exist. Okay, we have to keep that in mind for any fractions. It doesn't ever equal 0. That's not possible for me to solve that. When I solve over here and I square root both sides and isolate the x, I get x equals -2. Okay. However, we might take a note of this, and if we don't see it here, we'll see it eventually when we make our table of values. This is not in the domain of the original function. If you plug -2 in the original function, you would get something undefined. You'd be dividing by 0. So we know that there's not going to be an absolute min or max at -2. So again, you could realize it there, or you'd realize it again in a minute here when you're filling out your table of values. So I'm only going to really consider -3, and I'm going to consider 0. When I plug in -3, I'm going to get 1 over -3 plus 2, which gives me -1. When I plug in 0, I get 1/2. So I know that I have an absolute max of 1/2 at x equals 0 and an absolute min of -1 at x equals -3. All right, for our last question, we have a natural log, and then we also have a linear piece being added to it, and we're looking on the interval 1 to 5. So again, let's start by taking our derivative. The derivative of ln of x is 1 over x. The derivative of 2x is 2. And I'm going to set that equal to 0. In order to make this a little bit cleaner, I'm going to put that over 1, and I'm also going to get common denominators. So what I end up getting is 1 plus 2x over x. Now again, just like the previous problem, I have a fraction here, so I'm going to solve for where the derivative is equal to 0 and also where the derivative is undefined and doesn't exist. When I solve over here, I'm going to get -1/2. When I solve here, there's nothing to do with x equals 0. Neither of these are in the domain or in the interval that we're given here from 1 to 5. Okay, let's make our table of values here. So I only need to put in the endpoints, so 1 and 5. This is going to give me ln of 1 plus 2. We might already know ln of 1 is 0, so this is going to come out to 2. This is ln of 5 plus 10. And even though we might not know how to simplify that one, we should definitely be able to gather that ln of 5 plus 10 is something greater than 2. So therefore, there is an absolute max of ln of 5 plus 10 at x equals 5. And there's an absolute min of 2 at x equals 1.